Hello all, I'm Dr. Pravas Sanjanbal. In today's class, we'll discuss about some more different examples of what countable and uncountable set. Okay. So today we'll discuss about what set of all Turing machines. Set of all Turing machines are countable. Set of all Turing machines are countable. So how to prove that set of all Turing machines are countable? So we have written some steps. Using these steps, we'll prove that the set of all Turing machines are countable. How? What is the first step? First step, all strings of sigma. All strings of sigma means input alphabet. All strings of sigma are countable. Yes, of course, we have already proved in the previous classes how all strings of sigma are countable. Let here sigma value equals to 0. Sigma value equals to 0, 1. Sigma value equals to 0, 1. Then we can generate all combinations of what? Binary strings. For example, the sigma star equals to what? Epsilon, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, like this, and so on. Okay, these are the sigma star. So sigma star means all strings of sigma are what? Countable. We have already proved in the previous classes. Okay, this is the first step. First step, to prove means set of all Turing machines are countable. First step is what? We have to prove that what? All strings of sigma are countable over the input alphabet what? 0, 1. Over the input alphabet 0, 1. Okay. What is the second step? Here? Every Turing machine can be encoded into binary strings. We can write what? Binary strings. Every Turing machine can be encoded into binary strings of 0 and 1. Okay, this is a universal truth. Okay, every Turing machine can be encoded into binary strings of 0 and 1. Okay, suppose a Turing machine M1 is there. So we can also convert the given Turing machine as suppose like 0, 1, 0, like this. Let we can convert this one as what? 0, 1, 0. Suppose one more Turing machine M2 is there, we can convert this values at what? 0, 1, 0, like this. Okay. Since every Turing machine can be encoded into strings, binary strings, what? 0, 1, like this. 0, 1. Okay. What is the third step? Okay. Second step is clear. First step is what? All strings of sigma means sigma star is countable. All strings of sigma are countable. What is the second step? Second step is every Turing machine can be encoded into binary strings. This is the point. What is the third step? Set of all Turing machines. Set of all Turing machines is the subset of what? Sigma star. Is a subset of sigma star. That means M is the subset of what? Sigma star. M means what? M is the collection of, or M is the set of all Turing machines. M is the set of all Turing machines means M equals to M1, M2, M3, and so on. M is the collection of infinite number of Turing machines or set of all Turing machines. This one is the subset of what? Sigma star. Sigma star means, it just tell that what? First one, sigma star. Sigma star means all combinations of 0 and 1, all combinations of binary strings. Sigma star. Here, every Turing machine can be encoded into binary strings. So that's why every Turing machine into binary string means we can say that step 2 is the subset of what? Step 1. We can set by directly we can say that step 2 is the subset of step 1. So set of all strings means, all Turing machines is the subset of what? Sigma star. Because sigma star contains all number of binary strings. Sigma star contains all number of binary strings. Means this is the superset. We can say that sigma star is the superset. We can say that what? Sigma star is the superset. But here, every Turing machine can be encoded into binary strings. It does not mean that when we'll convert M1, we'll get each and every strings. It does not, M1 we can convert into binary string, M2 we can convert into binary string, M3 we can convert into binary string. It does not mean that we can convert each and every strings of sigma star. There are some rules, there are some means how to convert M1 into binary string. There are some rules and transition functions are there. Based on the transition functions, we can convert each and every Turing machine into encoded binary strings. Binary encoded strings or encoded binary strings we can convert. It does not mean that we can convert each and every string or each Turing machine into each and every number of means binary strings like 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, like this. We can convert each and every machine into binary strings. This is the point. Okay, simple point. Okay, so that means M1, M2, this number of binary strings must be the subset of what? Sigma star, because sigma star is the superset. It contains all numbers of binary strings. But in step 2, what? Turing machine means we have some limited number of binary strings. Here, this is the subset because we have what? Some limited number of binary strings, some limited number of Turing machines are there. But it contains all binary strings. Sigma star contains all number of binary strings. Okay. So here M. So finally we can conclude that M is always the subset of what? Sigma star. M is always the subset of sigma star. Okay. So now, since sigma star is countable, M is the subset of what? Sigma star. Every means any subset. Any subset means here subset is M. Since sigma star is countable, since M is the subset of sigma star, so M must be countable. We can say that M must be countable. M must be countable. Okay. So step 4 tells that what? Every subset of countable set must be countable. Okay. If sigma star is countable, we can say that a subset like M must be countable. So what is the step 5? Step 5 is set of all Turing machines are countable. Set of all Turing machines are countable. This is the step 5. It's very simple. Okay. So here again I am explaining. First we will prove that what? Sigma star is countable. Sigma star is countable. Okay, then we'll prove that, then we'll convert every Turing machine like M, set of Turing machine, M into converted into binary numbers or binary encoded string. Okay, since every Turing machine can be converted into binary encoded strings, so M must be the subset of what? Sigma star. Since sigma star is countable, so M must be countable. A subset must be countable. Okay, so set of all Turing machines are countable. This is the point. Okay, in this way we can prove that set of all Turing machines are countable. Okay, there are some important points here. For Turing machine, the existing, which one means the existing language is what? REC language. REC means recursive enumerable language. Sorry. This is REL language, recursive enumerable language. For Turing machine, the existing language is called as what? REL language, recursive enumerable language. We have already discussed about the recursive enumerable language in the previous classes. You can see here, there. Okay. Since Turing machine is countable, so we can say that all sets of recursive enumerable languages must be countable. Okay. and its subset. Since RL language is countable and its subset, what? REC language and its subset REC language, must all REC languages are countable, and its subset context sensitive language, CSL, context sensitive language, are also countable, and its subset context free language is also, all set of context free language are also countable, and its subset all sets of regular languages are countable. All subsets of regular languages are countable. And since RL language is countable, we can say that all sets of, means for RL language, the RL language, that which type of Turing machine exists? For RL language, non-halting Turing machine and non-halting Turing machine exists. Since RL language is countable, for all sets of non-halting Turing machine are also countable. Since REC language are countable, we can say that since REC language is countable, all sets of REC languages are countable. The existing machine for REC language is what? Halting Turing machine. Halting Turing machine are also countable. Since context sensitive languages are countable, the existing machine for CSL language is what? Linear bounded automata. Linear bounded automata are countable. Since CFL languages are countable, for CFL, the existing machines are what? Our existing automatas are push down automata. All sets of push down automata are countable. Since regular languages are countable, so the existing automata for regular language is finite automata. All sets of finite automata are countable. Okay, this is the important point. Okay, so set of all Turing means this is the proof of what? Set of all Turing machines are countable. So in the upcoming classes, we'll discuss about some different types of countable and uncountable sets. Okay, thanks for watching.